Welcome to this irregularly scheduled Transport Lab seminar. It is winter break at the University of Sydney, so these are ad hoc. We will return to our regularly scheduled programming in a few weeks. It is our pleasure to welcome Prateek Bansal from National University of Singapore. We'll be talking about data fusion and cross-city learning.
Thanks, David, for the introduction. So I'm currently an assistant professor at NUS, and my broad work is in mainly two areas. One is more on the econometrics and psychology and understanding the behavior, and the second is more at the system level. And today what I'm going to talk about is, from a travel demand modeling perspective, how different emerging data sets like transit smart card data or the cellular trace data sets, how those data sets can be useful for the travel demand modeling. And in the end, if time permits, I will also talk about some recent work that we are doing on cross-city learning and some of the open questions that might be interesting for you to think about as well that we are addressing. This is a joint work with Kua Wo, Seng Wu, and both are research fellow in my group. Moshmi and Swapnil are from public health, because a lot of work that we do is useful for epidemiology modeling as well. So that is something we are trying to translate to the epidemiology modeling. Paolo and Becky are helping us in deriving new insights from the segregation perspective and how these high resolution activity schedules can be useful beyond travel demand modeling. So that's why it's fairly interdisciplinary in that sense. So in the data fusion, I'm going to talk about mainly, yeah. I'm going to talk about two topics in terms of using the transit smart card data and time-dependent 2D matrices, but let's get started with the context first. I assume you're familiar with the travel demand modeling, and that there are two main components of when we talk about travel demand modeling. First is generating synthetic population. Let's say your city has a population of 10 million, then what we do is we try to create those 10 million agents in the computer and try to make sure that their demographic characteristics have similar distributions as the population. That's the first part. And second part is about generating their activity schedules, which includes their trip purpose, travel modes, departure time, and all aspects of the trips and the trip chains. Now, if you think about broadly this problem from a distributional perspective, then I categorize my attributes into four broad categories, where X is your demographic characteristics, Y is your travel modes, trip purpose, and maybe the number of trip chain length, and the S is the sequence of the origins and destinations, which is the spatial aspect, and T is the temporal aspect. So broadly, if you can estimate the joint distribution of X, Y, S, and T, then you can generate all activity schedules with demographic characteristics. Obviously, you need to also maintain the sequence. So sequence is equally important. But the challenge here is the S. If you look at specifically S, and let's say you're working at a spatial resolution of splitting the city into 400 zones, and let's say you're looking at the trip chain length of 4 trips, you have basically 8 origins and destinations, which means there are 400 raised to power 8 combinations. So in terms of spatial and the temporal resolution, the number of attribute combinations explode if you really want to estimate the probability mass function directly. So the problem that I'm trying to argue here is that the spatiotemporal resolution is quite high if we want to directly estimate this function. What we try to do is we estimate destination choice models, we estimate different type of models. Those problems are subset of this problem because you can get the conditional distributions from here. For example, destination location choice is what? Probability of S given XY and some subset of T. So all the mode choice, travel destination choice, all sorts of choice problems are basically subset. Once you know that this distribution, you can update that. Great. So that's what we are after in the end. how do we do that right now? We use the household travel survey data. But what are the challenges with the household travel survey data? So let's try to understand very in a basic sense what we are missing when we are working with the household travel survey data. So let's say we have a very simplistic example where we have 3 zones and we have a population with departing before 9 a.m. After 9 a.m., we collect household travel survey data sample. And what we see is from zone C to zone B, 200 people are going in the population before 9 a.m., but we don't see any people going in the survey. So that's a zero cell problem that we encounter in household travel survey data due to the low resolution. And this problem gets worse and worse as you split your spatiotemporal distribution across different demographic characteristics and other attributes, right? So household travel survey data has this issue of low spatial temporal heterogeneity because you have low sampling rates. The other issue is the low sampling frequency. I don't know about Sydney, but in Singapore, we used to collect data every 4 years, and things do change in every 4 years. After COVID, we are collecting every year. So that's better. But in addition to household travel survey data, these days we are collecting transit smart card data, and we are also obtaining from the cellular tourist data sets, the time-dependent origin destination matrices. So the question is, for agencies, what is exciting is, can we reduce the sample size of household travel survey data set because you have these new data set which have higher spatiotemporal resolution? From the data source perspective, if we compare the household travel survey data set, which is HTS, and passively collected mobility data set, which is PCM, if you look at the sociodemographic, activity purpose, and travel mode, the joint, in terms of the marginal distributions and joint distributions, they are very well represented in the household travel survey data set, but barely observed in passively collected mobility data set. Maybe some age or gender you might observe. When it comes to spatiotemporal attributes are very low resolution in household travel survey data set, but they're very high in the passively collected mobility data set. So basically, there is a value here in terms of fusing these data sets because they are complementary in terms of what they bring to the table. So I'll be talking about 2 main applications on first combining household travel survey data with smart card data to derive the time-dependent OD matrices for all travel modes. And second is, once you get these time-dependent OD matrices, how do you combine them with household travel survey data to generate activity schedules? Given I'll be talking about these 2 studies and cross-city learning, I'll be talking more at an intuition level rather than going too much into the mathematical details. But some details will be needed for sure. So let's go to the first problem that we have. So the underlying assumptions in this problem is you have a comprehensive and reliable observations of transit smart card data, which is your source mode. And that gives you a good coverage of the time-dependent OD matrix for the transit. That's assumed is given. It's true for cities like Singapore, Seoul, London, where they have a good transit coverage. If you have a tap in and tap out data, then you can get it exactly. If you don't have a tap out data, then you have to estimate you need to go through some estimation. But the cases that we are considering, which is Seoul and Singapore, we have the exact OD matrix for transit. There is no errors there. What you have, and we call it as a source mode. Source mode is our transit data mode. From the household travel survey data, you still get the OD matrices across time, but they are highly sparse. If you look at your, this is the source mode OD matrix and target mode. So if your source mode is transit, your target mode can be private mode, your target mode can be just the whole non-transit mode. For simplicity, let's consider the non-transit. So the question is, how do you get these two sparse matrix of the transit mode and the non-transit mode? We have a very comprehensive matrix of the source mode. How do you combine these 2 things to get the very comprehensive mode of the non-transit mode, which is our target mode? So I'll talk about very briefly about some notations, and that will clarify. The fundamental approach is very simple. It's just a basic scaling that we are doing here. But I was surprised at why this has not been done. Maybe it has been done in practice, but I haven't seen anything in the academic literature. Okay, so I is our target mode. W is origin destination pair. K is the time. Time can be 30 minutes, 1 hour, depends on the resolution you're considering. So we define two important things. One is beta IWK, which is the ratio of the target mode share and the source mode for the OD pair W and the time period K. Okay, that's your beta IWK. And just to be, it's important that we observe this in household travel survey data, but maybe for less than 10% of the OD time pairs, not for everything, not for all OD time pairs. Okay, that's important. The second quantity is gamma IWK, which is also equally important. What gamma IWK is, for that, for ODW and time period K, how many observations are available for the target and the source mode? That's what gamma IWK is, right? So if gamma IWK is large, for example, you have 100 observations, then maybe your estimate of the beta for that OD time pair is better. But if your gamma is very small, like for example, for that OD time pair, you have only 5 observations in household travel survey data, then your estimate of beta will be quite noisy. So gamma is important in terms of how good beta is, okay? For those 10 to 10% of the OD time pairs that you observe in household travel survey data set. So basically, you have a very good estimate of the true travel demand of transit, NSRC, not the estimate, you observe the true value of NSRC WK. If we can estimate this beta well, right? If we can estimate this beta well for all OD time pairs, then all we need to do is we need to just multiply it with the transit demand to obtain the non-transit demand for those OD time pairs. So the goal is to estimate this beta hat well, basically. How will we do it naively? If we need to do it naively, basically we can just do any supervised learning approach. You can use the features of the origins destinations, and you can look at the connection between that beta that is observed for those OD time pairs, and you just run a regression. Okay, you can do any complicated supervised learning. That's not the point. But when you do that supervised learning, you are working with the noisy betas, right? So we do one more layer on that. We do some aggregation, smart aggregation strategy here. How do you aggregate better? So how do you get the better estimates of the beta first, and then you do the supervised learning? So that's why we call it adaptive representation learning, but that's a fancy name. Basically, we are trying to aggregate some of the OD pairs for which you have the fewer observations, get a better estimate of the beta, and then do the supervised learning. Okay, so that's the crux of the approach. But the point is how good it is, whether it really works in practice or not. And that's where we spend more time in terms of understanding how good this is. So we do the validation in Singapore and Seoul. What you see here is we have the transit OD for Singapore. We generate the private vehicle OD, and from that we get the private person OD for Singapore. And what we have an external data from TomTom, which is a private vehicle OD. And these are the recovered one on the y-axis. And we condense the 2 dimension into the 1 dimension here for the origin, destination, and time. So these are the spatial dimension condensed in the 1 dimension. So if all observations are on the 45-degree line, then we say, okay, well, it's good. But obviously, TomTom is also not a ground truth. It's 25% of all observations that we have. So the point of showing validation exercise is what we are recovering in terms of the OD matrices for private vehicle over time is consistent with what we are seeing in the external data set. For interzonal and intrazonal OD time matrices, this is how the plot looks like. This is the departure time distribution plot. For Seoul, on the right-hand side is for the Seoul. So we are doing it for cellular data. So what we are doing is from the transit, we are obtaining the non-transit trips, combining them together and creating a full OD matrix. And then the validation is done against the cellular data. Again, cellular data is not perfect. The point of this validation exercise is to show that it's consistent with what is there in the external data set. and it's an acceptable range in terms of how well it does. But obviously, the caveat is this method works when you have a very good coverage of transit across the city because you need something to anchor on. But it's a very simple approach, works well. Then we use these generated OD matrices in the epidemiology models as well, and we show that how it improves the prediction of the spread of the disease, infectious disease. And we do some more applications of this approach. This is the spatial level validation of the same. We unpack this spatial dimension into the 2-dimension. And we are able to get it published recently in Nature Communications last month. Let's go to the second step, which is a sequence of this, because now you have OD matrices, basically, because from transit data, you have created the time-dependent OD matrices. Can we now combine them with the household travel survey data to preserve the distributions that you have for the attributes which are well presented in household travel survey data sets? And agencies like it more because they have the both household travel survey data and smart card data. So it doesn't depend on the proprietary data in that sense. For the validation, yes, but in addition to validation, it doesn't depend on the proprietary data. So that was one of the other motivation to work with the smart card data rather than other data sets so that we can really see if they can be used. And I'm talking to agencies in Singapore in terms of whether they want to use this in their workflows to reduce the household travel survey data sample size. So let's go to the time-dependent origin destination matrices. So time-dependent origin destination matrices, one way is to obtain from the first approach if you have a good transit coverage. Other way is you get from cellular operators, right? So if you have a good coverage of the cellular phone operators, telecom operators, then you can get from that. Another important thing is rather than getting trajectories, people are more comfortable in sharing the aggregated information on the mobility. So that's something which is useful. And it covers quite a bit high proportion of the population. But what are the issues if you look at the time-dependent OD matrices? There is no interdependencies between the trips, right? And you don't have the sociodemographic and trip chain attributes. So the good thing here is household travel survey data have all those aspects which are missing in the time-dependent OD matrices. It's about combining the value of those two aspects together. So typically how it is done, I missed the references here, but I can tell you there is a one paper from et al. That's by Oxhausen, and I can provide you references later. But how is it typically done? Let me first tell you and then tell you what are the issues the way it is typically done. So let's say you have a comprehensive time-dependent OD matrices, which we call TD-OD matrix from passively collected mobility data. The common approach is first you try to create the activity schedules which are statistically consistent with these time-dependent OD matrices. How do you do that? You fit any first order or second order Markov chain type of model, and you maximize the likelihood to match the OD matrix, basically. Broadly, that's the idea. And then in the second stage, you impute the sociodemographic characteristics from the household travel surveys. So that's the product. What is the issue in doing that? The issue is when you are generating these locations and the time, there is no contextual information. There is no information on the trip workers. There is no information on the duration. There is no information on the travel mode. So the issue is the spatial locations are already have no context when you're generating them. So they're likely to be not very physical when we generate them. In fact, those wrongly generated spatial locations will impute incorrectly the demographics characteristics as well later on. So what is the other way to think about this problem? The other way to think about this problem is how about we first do the imputation or fusion and then we generate the activity schedules, because once we do the fusion and then activity schedule, we can condition on all those activity purpose and all those. We still do the generation through the Markovian chain process, but the first doing the fusion will help you having the context that we need. So for example, you have a household travel survey data. You can convert it into a very sparse OD matrices for each demographic, travel mode characteristics, right? And you have a very comprehensive time-dependent OD matrix, right? So the idea is, how do you first do the fusion between these two, use the very high spatiotemporal resolution of the time-dependent OD matrices and the time-dependent OD matrices that you're getting from household travel survey data sets. Fuse them to first generate these comprehensive time-dependent OD matrices with demographic characteristics and the trip purposes. And then you use, in the next step, the generation using the Markovian approach. So I'll define a few things here, but will not go too much into detail of the notations. But remember, X was demographics, Y was sequence of the trip purpose and travel mode. Z, T, and D are related to the locations and time. Okay? Because we are converting these sequences into the time-dependent OD matrices, so this is just, we are converting this Z, T, D into the Z bar, Z tilde, T bar, and T tilde. These are basically spatial and time attributes for the time-dependent OD matrices. So to put things again in perspective more properly, what you observe is a joint distribution of X, Y, Z, Z bar, Z tilde, T bar, T tilde from HDS after converting those sequences into the sparse OD matrices. You get a joint distribution of the same in the passively collected data sets. There is no X, Y, K because that's not observed in the cellular data. The first step is you have these sparse matrices, these solid matrix. The first step is to generate this comprehensive joint distribution, X, Y, Z bar, Z tilde, T bar, T tilde. This is the fused distribution. What we want to do when we generate this fused distribution is preserve the joint distribution of X, Y, K and some low dimensional distribution of this. We will see how do we create this. So you can already see the latent class or some classing clustering is coming here. And we want to preserve this distribution of the passively collected data set as much as possible. Once we are able to generate this fused distribution, the next part is a little bit not that exciting. It's more of generation of the activity chains. But one thing to note is we can easily condition on the Y, which is travel purpose, trip mode of the previous chains when we are generating the next activity. So when we are generating the locations and time, you have more contextual information than first generating the spatial and temporal attributes and then imputing. But because this is hard, it's not easy to do it. We used to do other way around. So what's the idea? How do we do the fusion? Well, so the idea of the fusion is as follows. You have this joint distribution coming from household travel survey data set, and this spatiotemporal distribution coming from the PCM data. So what we do is we have an encoder which uses the features of the origin destination time. Then the encoder helps in creating that latent space, the coherent latent space, where it basically partitions the origin destination and time space in a way that you have a coherent demographic groups in that. And after creating this latent class, we have that decoder condition on this latent class, which helps us in creating the fused distribution. Those who are familiar with variational autoencoder, you can think of it as a variational autoencoder, but in a discrete sense. At the same time, when we are designing this, we ensure that some of the distributions that we have in passively collected mobility data set, which is the spatiotemporal, and XYK phi, which is a low dimensional spatiotemporal features joint distribution with the demographics and the social attributes can be as well preserved as we have in the household travel survey assets. So if you just apply the traditional variational autoencoders, then you might not be able to preserve these kind of distributions. So that's where, I mean, you can apply all those black box ideas, but I think it's important you to understand what you want to achieve in any data fusion problem that you have. So the encoder looks like some neural network because we are just training through an autoencoder framework. But what's important here is the loss function part is quite important. So we have two components of the loss function here, the way we design it. I'll not go into the math, but what we are trying to do in the first loss function is, as I said, we are trying to match it as close to as with the household travel survey data set, which is the first distribution that we have. That's what we are trying to do. The second one is the minimizing the probabilistic distance between the clusters in the household travel survey data and passively collected data set. So we have some theoretical properties which helps us in understand, and it seems intuitive after doing it that if the way you are creating clusters in household travel survey data sets and probability of clusters in PCM and STS are similar, then you are more likely to achieve these two conditions that we have here. But it is difficult to do difficult to achieve that simultaneously. So we try to not exactly achieve it, but minimize the distance between these two. And in terms of, if you look at the decoders, if you have these two decoders after creating those conditional latent classes, your joint distribution can be easily understood in this way. So there is an underlying assumptions while we are breaking this joint distribution into these two parts is conditional on the C. We are assuming that the X, Y, K, which is the non-spatiotemporal attributes and spatiotemporal attributes, but conditional on C, they are independent. So the whole structure is the first part is the variational autoencoder part, where we are trying to preserve these distributions and at the same time creating those latent classes, which helps in ensuring the consistency. And this is your generative process, which is after fusion, you have a contextual information so that the next activity is generated better. Again, we spend a lot of time on the validation. There is a simulation study, which I'll not talk about, but there is a Singapore case study and Seoul case study. In Singapore, we use the full household travel survey data as a household travel survey data. We use the time-dependent OD matrix that we synthesized in the last part. And what do we use for validation? In smart card data, we have an information on the senior and adults, which we don't use anywhere. So we kind of use the generated spatiotemporal patterns of the senior and adults for the smart card data. And we try to see how close what we are generating after fusing and going through the activity generation process, how closely do they match with for adults and the seniors. For the Seoul case study, we use the household travel survey data and the time-dependent OD matrix that we obtained from cellular signal data. But what we don't use we don't use any, because cellular signaling data have a good distribution of home and work locations. At least you can infer if you have a panel data. So that's we don't use. And we also have some information on the age group that we don't use in the fusion part. So we can use that for validation that how those heterogeneous patterns across age, how well we are able to produce. Because it's not just about increasing the heterogeneity of the data, it's also about how feasible it is when we are increasing the heterogeneity. So before I talk about the validation part, it's also important to understand what are we achieving in the end with this data fusion. So if you look at the unique location time combinations, if in household travel survey data, what you have is around 20,000 unique OD location time combinations. But when you look at what we are generating, the number of location time combinations is around 140 times of what we have in household travel survey. So basically, we're increasing the heterogeneity of the activity schedules that we are generating. Now, I only need to convince you that what we are generating is not garbage. It's feasible. It's a reasonable thing that we are generating. So let's try to understand this first for Singapore, where we have on the left, you have adults. On the right, you have a senior. So left 3 plots are for adults, right 3 plots for senior. And it's important to understand that the patterns of seniors and adults are quite different. So it's not just that because we are using smart card data, aggregated way, we should be able to produce these patterns naively. Okay. So smart card data is in the left arrival time plot is black. Fusion is a turquoise color, and HTS is a purple color with the dotted line. So let's first look at the departure time, arrival time distribution. So we can see that what we observe in smart card data in Fusion is much more aligned compared to even what we have in HDS, because these OD time, these origin destination and the time adjustments that we are doing, they also adjust some of the temporal distributions naturally. When you look at again, we are looking at the origins and the destinations, but they are converted into the one-dimensional space. So what you have is on the y-axis is smart card data, and on x-axis you have Fusion versus HDS. So the crosses, purple crosses comparison of HDS versus smart card data, and the turquoise circles are the comparison of the Fusion and smart card data. So if you're closer to the 45-degree line, that means you're producing much similar patterns that you observe in smart card data. And it's crazy similar, actually. It's much, much closer than household travel survey data than in what we are generating after Fusion, right? And not only for the adults, but if you look at the seniors, quality is better for adults, but it's still much more aligned for the seniors as well in the spatial and the temporal distributions. Okay, now we have a little bit more here for Seoul. So why do we have more? So these are for 3 trip purposes on the left: home, work, and others. On the right, we have for 3 age groups: age below 20, age 21 to 60, and age above 60, right? So what we are trying to, the lessons remain the same as we have seen in the past. Again, we can see that for home, work, and other, you can see the generated distribution, which is turquoise, is much more closer to what we have in the cellular trace data compared to what we have in household travel survey data set, right? And for different age groups as well, the patterns are quite different. But again, if you look at the 45-degree line, your round circles are much closely aligned with the 45. These are some of the spatial distributions in 2 dimensions also have been created. These are the cellular ones for the home. These are the generated ones. This is for the work. Overall, we could see that the hotspots and everything are very well aligned. So in summary, I think this is a 2-step approach. Our learning is, if you just try to throw things on a black box autoencoders, it doesn't work that well because you don't have control of the hard constraints. So that's important. It's important to first do the fusion and then do the generation. We have those results as well, where we can show that why this method works better in the paper. And it's about increasing the heterogeneity while maintaining feasibility. It's not just about increasing the heterogeneity. Okay? So that's important from the perspective of if you want to use this data for the developing models. So the next steps are related to this is to, earlier we used to develop models with household travel survey data. Can we use the synthetic data to estimate the models? And if we can do that, then obviously you can significantly reduce the household travel survey data sample size. We can show that even with the 20% of the total household survey sample size, you don't lose too much in the accuracy, basically. But we are working with Land Transport Authority now to see if we can really estimate their models using the synthetic data and still able to get similar results, or at least do not lose significantly of what they use household travel survey data for. Good. So in the next 10 minutes, I will talk about the ongoing work on cross-city learning. So the idea is, let's say you have data for 5 cities on OD matrices in the US. Can you generate the OD matrix for a city in India, for example, Delhi, right? So this is a very trendy topic these days. And commonly, there is a lot of deep learning work is happening, but what I want to tell you today is what are the open questions that still require a bit more thinking than throwing things in black boxes. So there are 2 recent papers on this topic. One in Nature Communications. What it does is it just uses the deep learning on satellite imagery data, which is available in in any city, for example, obviously the quality changes. Let's say that is available. So how do you use these features to do the mapping between the OD matrix and satellite imagery? And then for the cities where satellite imagery is available, you can use that supervised learned model to predict. That's a very simple paper. But it's an impactful paper. It's a useful idea. Second paper is about the similar idea. How do you reconstruct those OD matrices from the other cities? They use some physics-informed approaches. Again, a little bit more black box, but they try to do it for many cities and do validation. But there are 3 main questions which are still not answered and very important. The first one is, how do you find a good source city? What is the characterization of the good source city? And second important question is, at what resolution you need to transfer? Do you transfer the model learned from other city for all origin destinations in that target city, or do you do it at a different resolutions? So these are the questions which require a little bit more thinking than just fitting the model, basically. So let me start giving some examples on why this problem is not that trivial. So what I'm presenting here is, let's look at the 2 graphs that we have. So we have 5 target cities and the same as 5 source cities. Assume that for all those 5 cities, you have the OD matrices. So it's a thought experiment that we are doing. On the left-hand side, we are showing how well the models work. If we assume, for example, this is Los Angeles. If I use Chicago's data, let's say Chicago's satellite imagery data, and connect with the Chicago's OD matrix, train a model, and I use that model on the Los Angeles, then how well your model is doing is indicated by the value in this section, okay, in this cell. And what is this value? This is called CPC. It's a measure of how well you have predicted. It's a measure of TIJ is, let's say, original one, T tilde IJ is the predicted one. So it's kind of how well you predicted. So higher is better. So, and what is this 0.74? Let's say you use the Los Angeles trained model and you predict the ODs for the same city. So self-training. So all diagonals are self-training CPCs. So they will be higher because obviously you're training on the same structure of the city. So CPCs for the diagonals will always be higher, okay? Diagonal CPC is higher. Now we estimated one more thing, which is important, is similarities between the cities, right? So similarities between the city is, you can use any measure. Here we are using cosine measure. And similarity between the open access attributes. So one thing which I want to point out here, negative means less similarity, positive means higher similarity. So more green is more similar basically, and more red is less similar. So if you look at the San Francisco and Los Angeles, if you just look at the similarity-based matrix broadly at the city level, that's not very high. But if you look at the San Francisco, except self-training, if you use the model trained in Los Angeles, it predicts better than all other cities, the OD matrices, right? So what I'm trying to argue here, that it's not about similarity across all attributes. You have to think about the similarity of which attributes and in what sense, because the cities are very heterogeneous. You can't just take the models from one city and apply it to the other city. So another way to think about is, rather than applying models for the whole city the same model, how about we use the different source city for each origin in the target city? So how do we interpret it? For example, for Chicago here, what we do is we look at the different origins in Chicago. And because we know the true OD matrix of Chicago, what we do is we use the Boston model, San Francisco, Houston, Chicago, and Los Angeles. We use not the Chicago, but all other 4 cities. For that, each origin, we use their model and try to predict whichever is the closest. We use that, the best possible model. So what we are showing here is around 28% of the origins, the model from Los Angeles is better. For 56% of the origins in Chicago, model from San Francisco is better. So what we are trying to say is different origins in the city require different source cities. You can't use the same source city for the whole city. It's a no-brainer, but we can still see through the data that it's important. So we took a one step further just to clarify that the real data, it's not a true OD that we have, but we are using here data from Replica. Replica is use the census data as well as the cellular trace data and TomTom data and combine all these three to generate the activity schedule. So we are using Replica 8 ODs as the given OD in this case. Obviously, there is no ground truth data, so that's the best we can have. So what we have here is there's no way to hide it, right?
It's fine. Yeah.
This one?
Yeah.
Here? Thanks. So what we are showing here is, let's say you have a city level transfer similarities, city level transfer best missed, and the original level transfers. So what you have here on the 45-degree line with the city level CPC and origin level CPC, obviously origin level transfer is slightly better, but if you look at even R squares rather than the CPC, you see even larger differences. Similarity was off the charts, but even if you look at the city level transfers for some cities is quite bad. So this is the situation that we have here, but the question is, how do we find the different weights for the different source cities, right? So what we are working on is a very simple idea that how do we estimate the weight, given that you have a way to mapping between the open data set and the demographic. So there is an enough literature on how do you map the OD matrices with the open data set, right? So for a given source city, for each origin destination in the target city, you have these PIJST. If you use the model from the source city S, then what will be the PIJST, which is the probability that the trip originating from I is directed to J in target city T, right? For using that mapping that already exists, that you can use the gravity model, deep gravity models, or any physics informed models. Let's say you have this PIJTS for different cities. The point is, for that origin in that target city, how much weight do we give to that source city? That's over WIJTS, basically. So what we are saying is this weight, we can define it through a very flexible function. And we are working on the characteristics of this function, but right now this f theta can be linear as well, right? And the attributes that you have is the feature vector of describing origin I and target city T. And you have a source city S and the target city S. And what we are doing is, for the training data, we are trying to minimize the distance between this P hat IJT and what we observe in the PIJT. So it's a clear divergence between these two. And the hope is if you can train this better for, let's say, 50 cities, can you get it a generalizable model? Can you get this WIJ TJ to be generalizable in the cities beyond the training data set? But right now, I'll show some initial results using 50 cities. On the x-axis is the target city. On the y-axis is the weights for the different 50 cities that we have. And what is interesting is for some cities, we have higher weight across all target cities, basically. So that means there are some cities which have more characteristics in terms of sharing, providing the information. And when we look at the CPCs of across these 50 cities for the self-trained model, the best matched and the proposed one does reasonably well in terms of matching the self-training performance that we have. But there are many open questions, despite there's a lot of black boxes out there. The main question is what structural and mobility characteristics determine whether city is a strong or weak source of transferable OD patterns. And while I'm talking about all four questions, what is more important is how can you tell this transfer is good enough without knowing the actual OD matrix of the target city? Because if you have a OD matrix of the target city and then you are telling it's good, then it's not useful because then you already have the OD matrix of the target city. So we are working in that direction, that how do you test the quality of the transfer without even knowing the target city's data? So that's a very important question here. So what makes the OD structure of the target city easy or difficult to reconstruct through cross-city transfer? These are all open questions, even if it seems that there are 1,000 papers written on this topic. Can the transfer difficulty of a previously unseen target city be anticipated before its detailed OD flows are observed? I think that's the most important one, if we really want to make it useful. And the last one is what is the smallest and the most structurally diverse set of source cities required to preserve the near optimal transfer performance? So near optimal is the self-training. Self-training is the near optimal in this case. Great, so that was my presentation, and happy to answer any questions you have.
Questions online, questions from the audience.
Thank you for the presentation. And so my question is about the chain that you mentioned in the part of your presentation.
Yeah.
Maybe speak up so that the.
Oh, sorry. As you confused about why you need to use the Markov chain, because I think about like if you only want to combine it to the data set, like what's the role of the.
So because we need to in the end generate the activity schedule. So the question for the online audience is after fusion, why do you need to generate the activity chains? So in the activity-based models, the ultimate objective is to generate the activity schedules of the people, the daily activity schedules of the people. Because then we can say, oh, rather than generating the synthetic, rather than collecting the actual travel diaries, can you rely on these synthetic travel diaries, which are highly spatiotemporal, have high spatiotemporal resolutions, and which are consistent with the other data sets that we observe, not just with the household travel survey data set, basically. So that's the reason we have to do that second step. Thank you.
Online.
There's one online, just raise his hand, but
Yeah, you can.
Okay, go ahead.
just so for,
They can either.
no, I could just unmute himself.
Austin, did you talk to?
Yes, please go
Do
ahead.
you have any theories for why some cities, you mentioned that it could be structural or mobility characteristics that make some cities good and some cities bad?
We
Do
do
you have
have
any unfounded theories that you can share?
We do have it right now, but we are still working. It's work in progress, so I don't want to claim it yet. We are testing it in the cities beyond US.
Okay.
So I mean, it's good to do between US, but can we do from US to Colombia, for example, Bogota? So then I would be more confident in saying whether we have really cracked it, but still it's work in progress. But we are able to find some fundamental generalizable relationships.
Okay, so you mentioned you were doing modeling.
Yeah.
And by implication, longer term modeling. And all of what you're estimating in this cross-temporal stuff is at a single point in time, essentially. Why, even if it predicts well today, would it predict well in the future?
That's a very good question. So the point is, there is no reason that this will predict better in the future. But what it is saying is, let's say today travel patterns change, right? And you need to look at what's happening right now. First important thing is you can estimate better models with this rather than using household travel survey data because you have a synthetic travel diaries. So high spatial data.
Why do I want a better model? If I have the data, why do I want a better model?
Because you want to do the better forecasting.
Why do I want better forecasting?
To plan better.
And is there any evidence that better forecasting increases?
Well, then, I mean, that's a question which tells that travel demand modeling is useless. So if we go to that premise, yes, that's,
So I mean, understanding
I think
the
it's-
nature of the world.
it's
today
more of,
makes sense,
it's
but-
more of a scenario analysis that we use in travel demand forecasting. And we can get more realistic scenario-based analysis if we do the better, models, right? Second important use case is if you reduce the sample size of household travel survey data, maybe during COVID, you can't do 20,000 responses. You cannot collect to 20,000 households. But maybe if you need 2,000 households from surveys, you can update these patterns very quickly. Maybe it's not only just for the forecasting, there are many other applications. In epidemiology, you need very good mobility patterns. So we are so restricted and so narrow-minded, narrow-focused on the transportation. But these are used in real time by epidemiologists. They don't have very good transportation inputs. And they are using like transit data to do that. But if you can say that, okay, here is this current travel patterns. If we get small sample, we can update it and we can get a better estimate of how mobility look like right now. And that might help them better modeling us.
So you showed how much better the supplemented survey was with the better data. The supplemented household survey was with the better data.
Yes.
How good is it with just the better data? Can we predict travel demand without the household travel survey?
It's not possible because we don't have all the demographics and the
Do we need all of that in order to understand the travel demand?
They
We know
need
it
to, at least the age and gender is what they need because there's, at least in epidemiology sense, they need because they need to understand the exposure, how people react to the exposure is different. So they need to know those kind of estimates of, okay, how many gender, what is the age of the people that are traveling across city, and even if purpose is useful to them, they're getting there in terms of using all those dimensions that we have in their modeling.
My question come up yet?
Yeah, not yet.
Okay.
Okay. Other questions from audience?
Yes.
So in your model, that like beta and gamma,
Yes.
and there are two different metrics, and they include to one same encoder,
Yes.
but there are two different metrics.
Yes.
But
The number of the attributes that we use for encoding exist in both data sets. So it's kind of creating a clusters where you're using the attributes of the origin, destination, and time related attributes, which are observed in both household travel survey data and PCM data.
actually they are similar, or they are not that different.
The attributes are there basically, so we can cluster on those attributes.
Okay, and then it goes to the end. The new. Thank you. Yeah, this way. And I saw another slide. So after that, the metrics will go over again, right? It's a loop, kind of that. You generate it for, yeah.
So this is showing basically the loss function, which in the loss function, this or PC, HTS and PCM distribution, the JS divergence between them is minimized to achieve that. So that's why it is just an indication of that. It's a way of connecting the loss function. Yeah.
Okay. Any last questions? Any last questions online?
No,
Okay.
there's no one.
Great, thank you.
Thanks.